Hi everybody, I hope this video finds you well. In today's video, we're going to be taking a look at another example of running the most recent hypothesis test that we learned, which is the chi-squared goodness of fit test. Before we get into this example, I'd like to give a little bit of background about some of the data here, because this again is sort of based on a famous statistical case. What we're going to be doing in this is investigating the sort of distribution of days on which births occurred at a hospital. And the reason that this is sort of a famous example is that there for a while was an investigation across many hospitals in the US about whether or not doctors were sort of inducing labors on days like on Thursday and Friday to avoid being on call for a possible pregnancy or for a possible birth over the weekend. And one of the ways that this can sort of be diagnosed is through a statistical sort of investigation. So I want to look at how that would be sort of conducted so that you guys can sort of see this. So we're going to take as an example, if you want to investigate if the births at a local hospital are not evenly distributed amongst the days of the week. So notice that, if everything's sort of normal, the chance that you're born on any day of the week should be equally likely, right? As in other words, as a baby, you would have no idea whether or not it's a Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday, right? Each day would be an equally likely chance to be born on, right? But if something weird is going on, then maybe it's not evenly distributed. So we want to investigate if the births at a local hospital are not evenly distributed amongst the days of the week. So to do this, we are going to say that you randomly select 90 births from this hospital from the past year. We're going to assume that there were around 2,000 to choose from. And then we record the day of the week each birth occurred on. So we get the following data. So there were 10 births that occurred on Monday, 12 on Tuesday, 14 on Wednesday, 19 on Thursday, 18 on Friday, 9 on Saturday, and 8 on Sunday. If we check and we sum these up, 10 and 12, that's 22, 14 is 36, 19 would be 55, 73, 82, and 90, which of course we knew because we were selecting 90 births here. So we're going to carry out at alpha equals 0.05 a hypothesis test to test the claim that the distribution of births at this hospital is not evenly distributed. So our claim is that it is not evenly distributed. Then we're going to describe the type 1 and type 2 errors in this situation. So let's talk about how we'd approach this. So first of all, how would we identify the correct hypothesis test to use here? Well, again, the sort of key language that you guys should be seeing here is there's mentions of distributed or distribution several times here, right? We keep seeing distribution and distributed all throughout this. That should indicate a chi-squared goodness of fit test. So chi-squared goodness of fit. Another way to identify that this is chi-squared goodness of fit is to look at the variable that we're looking at, which is which day of the week the birth occurred on. Day of the week is a categorical variable, and the number of categories here, well, is Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. We have 7 options here, which is we've got we've got more than 2 categories, and a categorical variable, that's another indicator that this is chi-squared goodness of fit. So again, you can identify that this is chi-squared goodness of fit by the keyword distributed and distribution, or you can identify it that we are working on a categorical variable with more than 2 categories here. Either way, we should realize that we have a chi-squared goodness of fit. So let's talk about the hypotheses here. So my apologies, we should move that down real quick. Let's just go ahead. And then we'll remove that. This is going to be a chi-squared goodness of fit. Now we're ready to step 1, the hypotheses. So what is our null hypothesis here? Well, our null hypothesis is whatever the sort of baseline assumption is here. Now, in the previous example, our first example of chi-squared goodness of fit, the null hypothesis was sort of the previously assumed percentages, and usually those would be given to us in the problem. But if you notice, there's no previous percentages here, right? All we have is our actual data. Now, of course, we know that these data here, we're going to reference these as the observed counts, right? Anytime our data shows up, we know that those are the observed counts. So those are certainly not the null hypothesis. So what is the null hypothesis here? Well, we got to look at our sort of claim. We're talking about it being not evenly distributed. So what's the baseline assumption? What's our sort of baseline assumption if we didn't have any information? Well, we'd probably think that it is evenly distributed. So what does that mean? What does it mean to be evenly distributed? Well, we'd be saying that it's an equal chance that your birth would occur on Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. Well, since there are 7 days of the week, we know that an equal chance would be 1 out of 7. So our null hypothesis here is that the probability or the proportion that you get born on Monday is 1 out of 7. The proportion for Tuesday, 1 out of 7. The proportion for Wednesday, 1 out of 7. The proportion for Thursday, 1 out of 7. The proportion for Friday, 1 out of 7. Proportion for Saturday, 1 out of 7. Proportion for Sunday, 1 out of 7. Is this a valid distribution? Well, yeah, 1 out of 7 plus 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 1 out of 7. That's a lot of 1 out of 7s. Well, that's 7 1 out of 7s. That is 1. So it is a valid distribution here. So this is our null hypothesis. This is a very special type of null hypothesis for chi-squared goodness of fit that happens whenever you see something talking about being evenly distributed. All right, this is what the even distribution would mean here. If we were talking about months of the year for births instead of days of the week, well, then everything here would be 1 out of 12, right? Because we'd say that the chance you're born in any individual month would be equally distributed there. But in this case, since we're talking about days of the week, everything is 1 out of 7. What's our alternate hypothesis here? Well, we would say that at least one proportion, we wouldn't really say has changed because we're not talking about time frame here, but we would say is different. Now, what does it mean if at least one of these is different? Well, that means it would be not evenly distributed. So this alternate matches the claim that it's not evenly distributed. All right, what's our next step? Well, we got to get our expected counts table. And remember, the expected counts for chi-squared goodness of fit is going to be n times pi. Well, what is our n going to be here? Well, our sample size, as we know, is going to be 90. And the pi, well, is actually going to be the same for each of these. It's going to be 1/7. So let's get our expected counts here. For Monday, what is the expected count going to be? Well, it's going to be 90 times the proportion for Monday, which is going to be 1/7. And if we calculate that, we're going to say 90 times 1 divided by 7. You should get that comes out as about 12.9. So we would have expected to see about 12.9 births on Monday if everything was evenly distributed. What about for Tuesday? Well, it's going to be 90. And since Tuesday was also 1/7, it's going to be identical. 1/7, approximately 12.9. Is it going to be the same for all of them? Well, not in general for chi-squared goodness of fit, because in general, chi-squared goodness of fit often has different proportions for the null hypothesis. But in this case, they're all the same, so they're all going to be that 12.9. So Wednesday, 90 times 1/7, approximately 12.9. Thursday, 90 times 1/7, approximately 12.9. Friday, 90 times 1/7, approximately 12.9. Saturday, 90 times 1/7, approximately 12.9. And Sunday, 90 times 1/7, approximately 12.9. So all of the expected counts are going to be the same because our null hypothesis is that it is evenly distributed. All right, let's go ahead and move on to our conditions then. For our conditions, first one, random and representative. Well, that was stated, so we're all good there. Then we need to make sure that our sample size is less than 5% of our population size. Well, do we know the sample size? It was at 90 here. Do we know the population size? Well, we were told that there were about 2,000 births to choose from, so we can actually check this. N equals 90. Is that really less than 0.05 times 2,000? Well, that is 100. 90 is less than 100, so we're all good. And for condition 3, less than 20% of expected counts, less than 5. Well, we'd made 7 different expected counts. All of them were greater than 5, so we would say 0 out of 7. 0%, which is less than 20%, so we're all good. So all the conditions are met here. Now we're ready to move on to our test statistic here. We know that the formula for the test statistic is chi-squared equals the sum of the observed counts minus the expected counts squared divided by the expected counts. Well, the expected counts, of course, are going to be all these 12.9s from our table, and the observed counts, like we said, is our data. So let's go ahead and start getting these, but this time, just because this is about our 4th time of getting one of these test statistics, I'm going to write out exactly what you guys would need to show on an exam or a quiz. So the first component of the chi-square test statistic would be that we observed 10 births on Monday versus an expectation of 12.9. So 10 minus 12.9 squared and then divided by 12.9. First part of our test statistic here should be 0.65. Then plus, next one, we observed 12 against an expectation of 12.9. So 12 minus 12.9 squared divided by 12.9. So that would be 0.06. And then plus, next one, right? We observed 14 versus an expectation of 12.9. So 14 minus 12.9 squared divided by 12.9. Looks like we get plus 0.09. Plus, next one, we observed 19 on Thursday against an expectation of 12.9. So 19 minus 12.9 squared divided by 12.9. Should get 2.88 there. Then plus, we observed 18 versus an expectation of 12.9. So 18 minus 12.9 squared divided by 12.9 should be 2.02. Then plus, we observed 9 versus an expectation of 12.9. So 9 minus 12.9 squared divided by 12.9 looks like 1.18. And then finally, last one, the Sunday, observed 8, expectation 12.9. So 8 minus 12.9 squared divided by 12.9, 1.86. So 1.86 there. Sum all that stuff up, 0.65 plus 0.06 plus 0.09, then plus 2.88 plus 2.02 plus 1.18 plus that 1.86. Looks like we should get a chi-squared here, 8.74. So our chi-squared in this case, 8.74. Let's go ahead and get our p-value by taking a look at step 4 here. So step 4, we've got our p-value. We're going to need to use table D. Our degrees of freedom, well, is the number of categories minus 1. What is the number of categories here? Well, we had 7 days of the week, so it's 7 minus 1, which is going to be 6. Remember, our chi-squared was this 8.74. So we're looking at for 8.74 with 6 degrees of freedom. So if we do that, there's 6 degrees of freedom. 8.74 is going to put us right here between that 8.56, just over that, but below that 9.45, excuse me. And that means that our p-value is somewhere going to be between that 0.20 and 0.15. So that tells us that we get 0.15 less than the p-value, less than 0.20. So there's our p-value there. Then we can go ahead and make our conclusion. We take this p-value and we compare it against alpha of 0.05. This is somewhere between 15 and 20%. This is 5%, so clearly the p-value is much larger here. So that means we're going to fail to reject HO. So we're failing to reject HO. That means there's no evidence for our claim. What could we say that there's no evidence for then? Well, we could say that there's no evidence that at least one proportion is different, or we could say that there's no evidence that it is not evenly distributed. A little bit weird with that double negative, but absolutely correct way to phrase it. So, no significant evidence that the births are not evenly distributed. So, what would that mean in real life for our analysis? Well, I would say that in our analysis, right, we have no reason to believe that the births are not just randomly distributed. In other words, we would say that everything seems to be normal at this hospital. And notice that's true, even though, at least in our data, we did see sort of a spike in births on Thursday and Friday and a lower amount of births on Saturday and Sunday. But notice that what we basically found is that that's well within what we would see as normal variation when looking at a sample of 90 births. So in other words, even though this had a bit higher on Thursday and Friday and a bit less on Saturday and Sunday, it was well within normal variation, so there's no reason to think that anything weird is sort of going on here. Let's go ahead and wrap this up by talking about the errors. So for part B, we're going to talk about the type 1 and 2 errors. So as always, let's go ahead and just grab our hypotheses to make this a little bit easier. Always nicer to have the hypotheses when you're looking at doing the errors here. So there's our hypotheses. Can't get it to copy for some reason. There we go. So let's go ahead and pop that right there. Okay. Don't know which guy sort of came along with that, but that's okay. All right, so remember, null hypothesis, evenly distributed, alternate, not evenly distributed. So let's talk about what a type 1 would look like. As always, type 1 is reject HO, but HO is true. So rejecting HO means we're not going with the evenly distributed. We're saying that at least one is different. In other words, we are saying that there is at least one different or that is not evenly distributed. So significant evidence that births are not evenly distributed when in reality, what does it mean for HO to be true? It means all of them are 1/7, which means they are evenly distributed. When in reality, they are evenly distributed. Again, as always, when we're sort of thinking about errors, let's think about what the real life sort of consequences would be here. This is where we decide that there's evidence that the births are not evenly distributed. In other words, they're not occurring randomly, which might cause us to be concerned that maybe there's labors that are being induced when they're not supposed to be or something like that. So this would basically mean that we might investigate the hospital for some sort of malpractice, when in reality, they are evenly distributed. Nothing weird is going on. This, again, would be sort of a false accusation that maybe this hospital isn't treating its patients correctly here. What does a type 2 look like in this case? Well, a type 2, as we know in general, is that we fail to reject HO. That's our decision, but HO is false. So failing to reject HO means that we have no evidence that the births are not evenly distributed. So we'd say no evidence that births are not evenly distributed. And again, this double negative sort of language, no evidence that they're not evenly distributed, is the correct language. I know it's not grammatically the best, but this is the correct statistical way to say it, because failing to reject means no evidence. Well, what does it mean for HO to be false? That means this really is wrong, and it is not evenly distributed. When in reality, they are not evenly distributed. So what are the real life consequences here? Well, this is where we say we don't see anything going on. We basically continue to believe that the births are randomly distributed, but in reality, there really is something going on, and that could be major cause for concern if doctors are sort of inducing labors on certain days or something like that. Obviously, it doesn't imply that something is guaranteed to be going on, but it certainly would warrant some more investigation. But unfortunately, in a type 2, we wouldn't realize that further investigation would actually be necessary. In our next video, we'll be moving on to our very last type of hypothesis test called the ANOVA hypothesis test, which will bring us sort of full circle back to working with quantitative data instead of categorical.